Okay, so the idea of today's lecture is to move on, as I said, with the theory. In particular, we saw how to assemble the mass matrix of the overall body, starting from the mass matrix of the elements. Today, we will cover very straightforwardly the stiffness matrix, and then we will see the case of a 2D element, so the 2D body. We will specify our problem to the 2D case, because this will be of use for the last, let's say, subject of this section, which is going to be the completion of an exercise, which, as usual, will deal with the 2D case, because it's a little bit simpler from the practical point of view. In particular, we will really deliver all the inertia shape integrals and the mass matrices and so on of the different elements of a body, 2D body. And then there will be the last section, the last chapter of the course, which will regard reducing order models techniques. So all those techniques which are used to reduce the number of degrees of freedom of a model. When you deem that the model has not the need to be as rich as it is, so you can compromise its accuracy in exchange for less computational cost. Okay? So we can basically start as the definition of the stiffness matrix. Oops. Okay, so the stiffness matrix for the element, again, as you know, will deliver from the definition of the work of the elastic forces. So you start from the work, elastic forces for the element. The element J of body I. We already know. That's the virtual, actually, work. Can be defined as such. So it's a scalar quantity. And it's the opposite, of course, of the elastic energy, if you want. So on the volume Vij of the element, you have, adopting Voigt notation, sigma ij transposed applied over delta epsilon ij in the Vij, where this is the virtual deformation vector, and this is the stress vector in what we usually call as Voigt notation. Okay, so we introduce the constitutive relationship. Which we usually call as Hooke's law. And we have that sigma ij is basically C ij applied over epsilon ij, where this is the Hooke's stiffness matrix. So this is, again, a linear elastic. Constitutive law. Okay. Now we know that epsilon the vector of the deformation as such, as a vector d, I, please come in, the matrix Dij applied over the vector of deformation-induced displacement u over bar. So this is the vector of deformation-induced displacement. And this is a linear operator, linear differential operator. If you want, it's a matrix encompassing the derivatives. We have already seen it. For those of you who are not super familiar with that, again, make reference to chapter 3, where all of these things are treated in extensively. So this is a linear differential operator in matrix form. Okay, so from the theory that we have developed, what we have is that our vector of deformation-induced displacement can be written as n I j. Just a second. Okay. So it's the matrix n that we have defined in the previous lecture times the vector, the matrix B2 I times QFI. If you remember, QFI is the vector of the nodal coordinates of the overall body. In fact, it only has a subscript I. And so in this way, you can eventually be able to relate the deformation, the nodal coordinates induced by deformation to the displacement induced by deformation. Okay, so this is eventually what you get, and this can be defined as a new matrix n ij over bar times qf I, with again this n over bar ij, which is equal to n ij applied over b to I. Okay, it's just a way of regrouping. It's stuck somehow. Okay, just a second. All right, just give me a sec. Okay. Just a second. Okay. All right. Okay, sorry. Should be back online. And so this is basically n over bar ij is just a regroup of the matrix. Therefore, you can write that our vector of deformation is nothing else but dij, so our linear operator in matrix form, times n over bar ij times qf I. Okay, and therefore our virtual work of the elastic forces can be written as so minus qfi transposed applied over kffij applied over qfi, where this kffij, which is the structural matrix of the element, is, as you can easily imagine, something very close to what we have already seen. That's to say, dij n ij transposed applied over c ij applied over d ij n ij over bar in the bij. So basically what I did was only to put out of the integral sign those quantities, in particular the vector of nodal coordinates induced by the formation, which are not dependent on space but only on time. And this is eventually what I get. So if this is the virtual work, of elastic forces for element J, the overall virtual work of elastic forces will be eventually delta WSI, which, as you can see, is just the sum of the work done by in each element. So J going from 1 to the number of element NE, delta WSIJ. But this we already know how to write. No? It's minus QFI transposed, which do not have the J in superscript, times the sum from J going from 1 to NE of KFFIJ multiplied times QFI. No? And so this we can define again as minus QFI transpose KFFI QFI. So that the stiffness matrix of the overall body, again, very easily, is just the sum of the stiffness matrices of the element. Okay? So again, sorry, this is the structural stiffness matrix, just to be clear, because then there is a stiffness matrix as well. So the structural again, it's just the sum the linear operator transposed Okay, this is what we get. Now, if we define as vector Q I, basically, as usual, the vector all the coordinates, so r, theta, sorry, I'm not getting anything anymore. Just a second. Okay. If we define Q in such a way, we have that delta WSI, as usual, can be written as QI transposed KFF, no, sorry, not KFF anymore, just K, I times QI, where eventually K, I, is, as we know, just a composition of the structural stiffness matrix KFFI. Okay, so this is the stiffness matrix. While this is the structural stiffness matrix. Of the overall body. Okay, what is the difference? The structural stiffness matrix only refers to nodal coordinates associated to deformation. The stiffness matrix of the overall body is expressed, takes into account all of the Lagrangian coordinates, also the one associated to rigid motion, to which, of course, no deformation by definition is associated, and so no storing of elastic energy is associated, and therefore you can see that you have a singular matrix. Yeah? So the stiffness structural matrix is never singular. The structural matrix of the overall body is typically singular, because of course you have the chance of motion, unless you may have boundary condition or constraints in general that prevent your body from moving, and in that case the stiffness matrix and the structural stiffness matrix, they coincide. They are the same. Okay, basically. All right. So this was just how to assemble the structural stiffness matrix. As you can see, the structural stiffness matrix is much easier. In general, the stiffness matrix is much easier than the mass matrix. And the reason for that is that we are enforcing, again, a floating frame formulation in which In the mass matrix, you have encompassed all the effects of nonlinear couplings between deformation and rotation, and in general, the rotation and the translation are again encompassed in the mass matrix, right? Because your body is moving. If you were to consider an absolute nodal formulation, and if you wanted to develop, and you can try to do it if you want, if you were to develop the mass matrix in the absolute nodal formulation and not in the floating frame formulation as we are doing, you would notice the opposite. So you see now that in this case, typically for the limiting assumption that we have done, the stiffness matrix is a constant matrix. You see, it's just made of elastic constants. In N is a constant matrix because there are the most shapes, but eventually when you integrate them, they basically give you a constant value. D, the matrix D, is a matrix of basically derivatives. So once you integrate it, it's a constant matrix, your K matrix. While M, as we have seen, is highly changing, can change a lot. It has a dependence on the Q's. Well, if you do the same representation, but if you do it in the absolute nodal formulation, you would see the opposite. The mass matrices would be constant, the stiffness matrix would be highly nonlinear. Okay, can you figure out why that would be? I give you a hint on this. It's basically because, as I was saying, your point of view on motion does not follow, okay, your body in the absolute nodal formulation, because you basically describe all of the motion straightforwardly from the inertial frame, okay? And then you apply your forces on your body, and it's your force that has to follow your body, okay? So you have to, what is it that you have to encompass? Is the relationship between the forces and the change of orientation of the body with respect to those forces, okay? And this is basically what happens in the stiffness matrix. On the other hand, when you, like in our case, in the floating frame formulation, you adopt a local point of view, and then you report it eventually to the absolute frame. You do not see, in the hypothesis of a small deformation that we have always done, any change of mutual orientation between the forces and the body, okay? And that's why you have a constant matrix. On the other hand, you have inertial effects that vary with respect to the orientation and position of the body with respect to the inertial frame. And that's why you get a highly varying mass matrix, okay? So depending on which of the two formulations you adopt, you either have a variation induced by inertial effect or a variation induced by a variation in the mutual orientation of the forces, external forces, acting on the body. Okay. All right. Let's see if we can move forward a little bit. Yes, I think we can. This basically will serve as an introduction to the, as I was saying, the last part of this chapter, which is going to be an exercise, as we always do. And so we're going to deal with a 2D case. So because eventually our exercise will deal with a 2D application. So we can entitle this last paragraph as, let's say, planar motion of a deformable body. So what we have said so far is true for the 3D case, the most general case. Now we will just briefly give a hint to the 2D case, which, I mean, from a theoretical point of view, has no significant change, but is a little bit easier to treat, and that's why we will eventually deal with a 2D exercise for the 2D case. So we have the Pij dot, as we know, is Ri dot plus A dot I, sorry, not Ij, but just I, applied over R over bar Ij plus A I applied over R over bar dot Ij. And this eventually can be written as such. As we already know. Okay, so the dot, the time derivative of R over bar, eventually only encompass the deformative contribution of R over bar. We have that A dot I R Ij can be written as such. The derivative with respect to theta of I times R Ij times the derivative of theta with respect to time is the chain rule of differentiation, okay? Okay, I'm just expressing the time derivative, no? Because we know that A only depends on the rotation. And so when I derive with respect to time A, I'm deriving with respect to time theta eventually. All right, so we eventually have that P Ij dot can be rewritten as such. Okay. With this definition of the velocity vector, we can eventually rederive the mass matrix through the definition of the kinetic energy. So we can Pij and eventually the mass matrix. Oops. Okay, sorry. I think that of the element. Okay, of the mass matrix of the element. This basically will serve, this result will serve as an introduction for the exercise that we will deal next time. In the last few minutes of today's lecture, let me just try to maybe I can eventually, I don't know if I can, no. Just a second. It's better that if I use this so that everyone sees also from home. Okay. Okay. Let me share the screen also for home. Okay, so the last few minutes of today's lecture I wanted to dedicate to the assignment. The assignment will regard the modeling and the post-processing of a payload release mechanism. Okay. The idea, as you can see here on the right, top right part of the slide, is to monitor and model somehow the release of a multi-payload, let's say, case, in which you have, in this case, 2 satellites being released. It has to separate from the payload adapter, and you have to basically introduce some modeling elements, and you have to tune some of the rigidities and densities and so on of the model, so that some requirements are fulfilled. These requirements are that the maximum duration of this full maneuver of the release is 10 seconds. So you cannot, give a motion which lasts 100 seconds so that it's so smooth. Okay, it has to be done in 10 seconds. You have to avoid the excessive nutation and spin, and then you have the max spin rate.
Prof, scusi, da casa non si vede nulla.
Ah, allora un secondo. Adesso? Adesso si riesce a vedere?
Ora sì, grazie.
Ok. Allora, stavo dicendo che l'idea è quella di riuscire a modellizzare questo release riuscendo a soddisfare questi requirements. Quindi, maximum duration of the full maneuver, 10 seconds, max spin rate deve essere inferiore a 0.5 degree per second, and then you have to minimize the nutation. Ok? E la minima distanza, diciamo, tra i payload, tra i 2 payload, deve essere almeno di 1 metro. Okay, minimum distance at the end of the analysis must be at least 1 meter between the two, so you have to avoid collision. Okay. So what you will be required to model is basically the push-off springs, so the separation springs, as force elements, the tie-downs using bushing elements. You will have to define the thruster force, okay, as S-force elements. And then you, as a function of time, you have to define the parameters of the release mechanism, like the stiffness, damping, and releasing time. We have said at least 10 seconds for the overall maneuver. And you can change the density of the payload according to an assigned percentage, okay? So that eventually you will basically tune the model, okay? So there is, again, a part of the assignment which requires really the introduction of some of these modeling tasks, of these modeling elements, sorry. You can, for example, use different strategies to vary, to model your elements, like the S-force, you can use a step function, an if function, whatever. We have seen more than one of these possibilities. And the target is, again, to design the release mechanism, evaluate the performances, the displacement, the velocity, the angular velocity, the forces, okay, which insist on the model, satisfying the requirements on the pilot release, the limit spinning, notation, avoiding collision. the deliverables that you will be required to deliver. The final model will be the CMD file. So I don't want the simulation. I want the command file and the text file, plus the parasolid file. Okay. I want that you display the displacement velocity of the payload's center of mass, the angle and the angular velocity of the payloads of the center of mass always, and the time history of the spring force, the tie force, the thrust force. Okay, so there is some these are the minimum. Then you can, if you want to deliver more than this in terms of results, you can, of course. You will have to deliver then a report, so the model and the report, okay? On Word, on PDF, or PPT, whatever. You can also do a presentation if you want. It's fine. If you want to include a video, for example, you can, as you know. And the deadline will be the 6th of June, as we have said. Okay, so you will see that most of the model, because I will give you as an input the CMD, okay, of the model. So everything is already modeled, but those elements that you have to introduce, like the forces and the bushings and so on. And then we'll give you, of course, this presentation. We'll put everything on Teams so that you will have all that you need to deliver the assignment. As I was saying, the assignment is, I would say, rather simple. You will see it's not a big deal. So I did this also to take into account the fact that the time that you will have to complete this is not super long. So this has been taken into account. But again, the idea is through this you put your hands at least on something that is attendant to what we have seen. Already today I will put everything online, but so that you can start familiarize and exploring the model. But before actually starting, you will see that there is a variable, which is a design variable that I designed, so that each group will have slightly different input parameters. Okay, so in terms of densities and stiffnesses and so on. Okay, so that each one of you will have slightly different results. And the idea is that next lecture, I will require everyone to be in class so that you can form group, and I will assign the design variable to each of the group so that you will have your own input model. Okay, again, it's nothing transcendental. Okay, it's something very simple, but still, you will have the opportunity to put your hands on something which is approaching reality. Okay. Here I put some, some hints on what on the elements that you will be using. So measures, design evaluation, tools, construction elements. Here, this is the parameterization that I was mentioning. And then you can put sensors if you want, and you can, of course, you will be required to extrapolate some post-processing results, so graphs, videos, if you want, and put that into your assignment. This is pretty much it. There was a thing that I wanted to say, but yes, of course. For all the help, you can make reference for sure to Mr. Catelani. So you already have his email. Do not hesitate to contact him in case of questions or troubles, okay? Because eventually he will be the one that will evaluate your assignments and will communicate me the grade of your assignment, okay? So this was just meant to present you a little bit of work. I will put everything online by today. You will already be able to explore it, but on next Thursday, we will discuss everything more into details. Okay, I will probably also, if I'm able to prepare it, also show you a video on how it works, okay, to let you see what I expect from you. Okay. All right, this is it.
What do you mean by minimize mutation?
Well, mutation meaning it's the spin, and so it's the spin rate and also the angle itself. So you have to maintain the orientation, and in case of spin, this change of spin must be minimized. Okay, both the velocity and the angle must be minimized. Okay, so it has to be it has to retain as much as possible the initial orientation. Okay, of the payloads I'm talking. Okay. Okay. So this is it. If there are no questions from home, I will stop the recording here.